All right, students, I got some induction videos I'll make. This is the first exercise in exercise 1G. This cute little diagram that was giving some of you some trouble, where we had a square of green dots and a square of red dots inside it. So that's figure number one, and then figure number two, like so. So there's always two squares. Figure number three. Ooh, that's not a good square, but we're going to pretend I drew a good square. And then inside of that, another square. So the point here is that there's always two squares that are being added up. So for figure number one, if you look at it like squares, you have a 2 squared plus a 1 squared. Over here, you have a 3 square plus 2 square. Over here, it's a 4 square plus a 3 square. Then they ask you to add them up along the diagonals. And what you should notice, those are some sketchy diagonals. What you should notice is that along the diagonals, you're adding up odd numbers. So this 2 squared plus 1 squared has to be equal to 1 plus 3 plus 1. Here it's 1 plus 3 plus 5 plus 3 plus 1, 1 plus 3 plus 5 plus 7 plus 5 plus 3 plus 1. Okay. So basically, the conjecture here, remember that this is figure number one, figure number two, figure number three. So my conjecture is that if I look at it as squares, then I have n plus 1 squared plus n squared. And if I look at it as odd numbers, I have the first n odd numbers plus the first n plus 1 odd numbers. So if you think about it here, I'll use a different color. Here are the first two odd numbers. Here's the first odd number. Here's the first three odd numbers. Here's the first two odd numbers. 4 odd numbers plus 3 odd numbers. And so if I want to write that up here, then I want to write the sum. Oh, I didn't mean to go to red. Let's go to black here. So the sum from k equals 1 to n plus 1, the first n plus 1 odd numbers, 2k minus 1, plus then the sum from k equals 1 to n of 2k minus 1. You might be wondering, why did I do 2k minus 1? A lot of times in class I've written 2k plus 1 because I like positive numbers. I did 2k minus 1 so that when I plugged in 1, it matched up with the first odd number. So 2 times 1 minus 1. If I did 2k plus 1, I'd be off by 1. I could still do it. I just didn't. I just wrote it 2k minus 1. So when I plugged in 1, it gave me the first odd number. When I plugged in 2, 2 times 2 minus 1 gives me 3. Okay, great. So then what we need to do is try to prove that one side equals the other side. You could go from either direction here. I am going to go from the right-hand side. You'll see this abbreviation in the textbook, RHS. So I'm going to make the right-hand side look like the left-hand side. Okay, so one way that I could combine these two series together, because they're really the same thing, just with one extra term, is I can just bust out the n plus 1th term here. So I have 2 times n plus 1 minus 1. And then the other n terms are going to match up. So I have 2 copies of the series. Because after the n plus 1th term, all the other terms match up. What I'm really doing there is I'm just saying the middle dude is the only one that is unique. The other odd numbers are showing up twice. Middle dude is unique. Other odd numbers are showing up twice. So here's the middle dude being unique. Here are the other odd numbers showing up twice. Okay? So then what I want to do is think about the arithmetic sequence. Odd numbers are an arithmetic sequence. And so remember, our arithmetic sequence sum is n over 2, a1 plus an. Or there's another version of it, but I'll do that version. So I have 2 times n plus 1 minus 1. I guess I could have done something with that. Plus 2 times n over 2. The first term is when I plug in 1. The last term is when I plug in n. And that's that. Now I'm going to move my face over here. So what do we get? Let's multiply a bunch of stuff out. We get 2n plus 2 minus 1. 2 and 2 cancel. 1 and 1 cancel. Plus 2n squared. And I guess what I'll do is bring it up here just to have a little more real estate. So I have 2n squared, 2n squared plus 2n plus 1, which I have a goal because I'm trying to prove it directly. I can write that as n plus 1 squared plus n squared. This n plus 1 squared comes out to be n squared plus 2n plus 1, and then the extra n squared is right there. And so that's my direct proof. When you're doing a direct proof, you're working with one side and making it look like the other side. Technically, I will mention, you could have started with the left-hand side and made it look like the sum of the two different arithmetic series. That just might have seemed a little bit more magical and less intuitive. Okay, so speaking of magical, let's do the same thing, but let's do it with induction instead. So what we're going to do is we're going to take our hypothesis, and our conjecture was that, what was it? 2 times n plus 1 minus 1 plus 2 copies of the sum from k equals 1 to n of 2k minus 1 equals n plus 1 squared plus n squared. Okay, so first step is we make n equal 1. What does that look like? The left side becomes 2 times 2 minus 1 plus 2 times, there's only a single term there, 2 times 1 minus 1. And if I did everything right, we need to make sure that this comes out to be the right side. So does that equal 1 plus 1 squared plus 1 squared? Hopefully I wrote it out correctly. So we have 4 minus 1 plus 2 times 2 minus 1. Over here we have 2 squared plus 1. So here we have, I guess I could just write 3 plus 2 times 1. Over here we have 4 plus 1. So we have 5 equals 5. Step 1 is okay. So what I'm going to do now is assume P of n is true. In other words, assume this statement is true. Then what I'm going to do is look at the n plus 1th term. So I'm going to only work with the left-hand side here. So I have 2 times n plus 1 because I'm going one step further, minus 1 plus 2, sum from k equals 1 to n plus 1 of 2k minus 1. Now what I'm going to do is try to make it look as much as like the induction hypothesis as possible, because I want to use this here. So I'm going to do a weird little distribution where I just distribute the 2 to one of the ones, but I leave the rest of it combined. And I'm also going to do a thing where I just break off the n plus 1th term there. So I have 2 plus 2 times 2n plus 1 minus 1. So that's breaking off the n plus 1th term. And then what I have left over is exactly my induction hypothesis. 2 times n plus 1 minus 1 plus 2k equals 1 to n of 2k minus 1. So again, I distributed the 2 to one of the ones and moved that in the front here. I distributed the 2 to the n plus 1th term and wrote it here. Then I gathered the rest of this term, and I gathered the rest of that term. And the reason I did that is I can use my assumption on this part. So I'm going to multiply out the terms on the left, giving me 2 plus 4n plus 4, excuse me. This 2 times 2 times 1 minus 1 plus the induction hypothesis, n plus 1 squared plus n squared. Multiply everything out and collect some like terms. So the n plus 1 squared is, well, actually, let me think if there's a clever way to do this. I can't see quite a clever way to do it. So let's just multiply everything out and hope it works. So n plus 1 squared, I'm going to put that in the front. That becomes n squared plus 2n plus 1. Then I have another n squared. Then I have a 4n. And then I have 2 plus 4 minus 1 plus 5. And what I want to prove is that that becomes n squared plus 2 and n squared plus 1. I think I may be 1 off. Yep, I see my mistake. So what I'm looking at here is, I'll show you how I figured out I made a tiny error. This right here is n plus 1 squared. And this right here is almost n plus 2 squared, but this should be a 4. So then I started looking back at my work to see where I made my mistake. And I made my mistake right back here when I distributed the 2. I didn't distribute it to this one right here. So let's change that to a 2. Change that to a 2. That brings that down to a 4. And so this is something that's nice, is I know what I'm trying to get to. I know I'm trying to get to an n plus 2 squared and an n plus 1 squared because I'm going to the next term. And so I knew exactly what I was looking for. And so even though there's a lot of algebra going on, I knew that I needed to see a 4 at the end and not a 5. And so after making that switch and fixing my work there, I can see that it's n plus 1 squared plus n plus 2 squared, and by induction, I'm done. All right, please comment if you got lost there, and I'll make another video help out. Thanks.